going to present my work on the modeling of electrochemical impedance spectroscopy in hollow solid-state batteries using FEniCS, obviously. So I'm a first-year PhD student, and my work focuses on the modeling of solid-state batteries, and more precisely on the modeling of the degradation phenomena in hollow solid-state batteries. So in my lab, we work on thin film batteries, so or micro batteries if you want. So as you can see, the dimensions are quite low, tens of micrometers. So application goes from L sensor, autonomous sensor to micro robots. In each of these applications, reliability is critical. So we want to mitigate the degradation phenomena, and we want to be able to predict the performance of the battery during its life. So thanks to the literature, we know that most of the degradation phenomena arise at the interface. And in my lab and in most of the lab, we use EIS, or electrochemical impedance spectroscopy, to characterize this degradation. So it's a non-destructive technique which involves applying sinusoidal perturbation on the battery and measuring the shifted outputs. So in this work and in general, we apply variable voltage and measure the shifted currents. And we compute the impedance at each frequency, so we strip the frequency. It's a really interesting technique because it gives direct insights on the evolution of each component of the battery during its lifetime. For example, we can isolate what happened in the bulk electrolytes, so yeah, right here, and what happened at the interface. So it's great to see the evolution of interface, for example, the resistance of the interface. But the first question is how to model a microbattery. So in this work, I use the reference model, which is called the PNP model, or Poisson-Nernst-Planck model. So we want to model ionic flux in this electrolyte for the moment. So it will be on a 1D domain. And we use the conservation equation that you can see right here. And the second equation that we want to use is the Planck-Nernst equation, or drift diffusion, which will solve the ionic concentration profile in the electrolytes. So we inject this flux in the conservation equation. Then we use the Poisson equation, which will solve the electrical potential. And as you can see, this is a highly coupled PDC system. So modeling the response of the electrolytes to a variable solicitation can be computationally prohibitive because, let's say, for example, you want to model perturbation at 1 Hertz. EIS range from 1 megahertz to millihertz range. And you want to model 1 Hertz, you want to model ionic flux on 1 second, of time. It can be really long and it's maybe not the best way. So I wanted to see is there another way. There is. So the first thing that we want to do is to translate the system into a dynamical equation and to solve the steady states. So EIS is performed around a stabilized state, equilibrium state if you want. So the PNP weak formulation can be translated into this equation with M the mass matrix, F is the residual vector, and U is the solution vector that will contain the profile, the concentration profile and electrical potential profile in the electrolytes. Then we want to solve the steady states that we can solve with a Newton-Raphson solver. And yes, okay. So this is simplified steady states. So we have the concentration profile right here across the length of the electrolytes, and the potential profile across again the length of electrolytes. So here I only model 20 nanometers, but usually we model more than like 1 micrometer or tens of micrometers. But it's just to show that, let's say, for example, we polarize the electrolyte with 100 millivolts, we will repel the ion from the interface. So the potential is applied here at this interface, and it will accumulate ion on this interface. So this is the steady state, and we will simulate EIS around this steady state. So the second step to do is to express the solicitation. So we know that, again, EIS probes the system by superimposing a smaller perturbation around the steady state again. So this mathematically translates to this equation with a complex amplitude right here. If we inject it in the dynamical equation, we have two terms that we can simplify. The first term, spatial term, with J is the Jacobian of the system, and the second term, the frequency-dependent term, with still M, the matrix term. So what we obtain is a frequency domain linear system, which is more easier and more quicker to solve than the time-dependent domain. So again, J is the Jacobian. You calculate it using UFL derivative. So now again, to compute the impedance, we need to calculate the currents. So we apply a perturbation. We apply perturbation with an amplitude of 1 millivolt, for example, and we want to calculate the current as interface. So in a battery, there is two contributions. So there is a Faraday current, which accounts for the charge transfer across an interface, for example, or across an electrolyte. And there is a capacitive current, which accounts for charge accumulation or depletion. So the first step is for each frequency, we assemble the system and we solve this. So we obtain this vector right here, which again contains all the complex amplitude of concentration and electrical potential across the domain. Then we re-inject this vector. We re-inject this vector into the frequency domain operator, and we obtain the global residue of the system, which is equal to 0 everywhere in the electrolytes, except for the first and the last elements, where we apply a boundary condition. And by projecting this residual onto a gate function that only account for concentration and for electrical potential, we can calculate the Faradaic and capacitive contribution of the currents. Then we can compute the impedance at each frequency. Okay. So here we have a Nyquist diagram. So this is the common representation when you perform EIS. So we plot the imaginary parts of the impedance against the real parts. And we have kind of two semicircles, the first one here and the second one, which is a little bit flattened. So each semicircle here corresponds to RC circuits with a specific time constant. And the first semicircle is for the electrolytic impedance, so for the bulk of the electrolytes. And the second semicircle, which has longer RC, account for charge transfer impedance. So what happened at the interface, for example. So here we cycle the battery and we perform IES at each cycle. And what we see is that the contribution of the bulk is not really growing or evolving. However, the contribution of the interface, the charge transfer impedance, is growing with time. It means that the resistance of the interface is increasing with the cycling. So now, if I use the PNP model and I model EIS around steady state, I obtain this, the Nyquist diagram. So qualitatively, we can reproduce both semicircles. Still, it's not flattened because there is, in real life, you have inhomogeneities, defects at the interface, which can explain the not perfect form of the semicircle. But we can still qualitatively reproduce experimental data. And we can perform this in like half a second instead of solving the model for thousands of time steps. So simulation of EIS was implemented, so using FEniCS. It's really quick, to be honest. We can do parametric studies with that in less than 1 minute. We can study the impact of several parameters. So it's really a great tool to link each parameter and its evolution, or each new hypothesis, with the experimental data. So my goal would be to study a more advanced version of the PNP, already under investigation, and why not coupling degradation law to study the evolution of the Nyquist diagram and trying to calibrate the model to reproduce the degradation curve that we see in real life. So thank you for your attention. And,
thank you very much. And also, again, never mind. But if you're ready, the next speaker. So thank you very much. Really great presentation. Any questions from the audience?
Yep. Thank
I mean, it could be. I don't really know. I'm not an expert in that, but it could be. It could be used because you can compute any flux. I want to say. So maybe, but still, it's just the beginning. And for the moment, we only use it on a battery system, solid-state battery system.
Any more questions? Maybe I can take the opportunity. So the impression is that with FEniCS everything is very simple and fast. But you mentioned some challenges, but maybe I interpret them maybe as modeling challenges or understanding. Do you see any sort of computational challenges or any, what do you say, future plans in terms of computation to?
To be honest, in my second year or third year, we want to model 2D or into 3D. I don't know how this technique will translate into 3D. I know that some PyBAM, people who made PyBAM, it's a library to study batteries, and they use a finite volume, and so they can compute. It's easier than this technique, but I know that there is challenge to go to 2D or 3D. So I don't know how it will translate, but for the moment it's only the beginning, so I don't have really lots of challenges for the moment.
But typically the competition is too expensive, so you sort of that's a challenge. But once you get very fast computations, then the natural next step is usually like optimization. Maybe you want to design something. Are you looking into that? Because then maybe you need to run like 100,000 simulations.
Yeah, we want to calibrate the model, so we have lots of data. It's micro battery. You have like tens of thousands of them on a single wafer. So we have lots of data, and we want to do, for example, Bayesian inference to have the probability distribution of each parameter. And to do so, we need to be able to do thousands or tens of thousands of simulation. And this is EIS, or Nyquist diagram, is the direct link between experimental data and simulated data. So we need to be able to perform against thousands of EIS experience. So since it's fast, it's a good thing.
Perfect. Very nice. Any the last chance for a question? Otherwise, let's thank the speaker again.